zoom over to my whiteboard. Good afternoon. Here we are. And we're going to do a kind of overlap. We're going to look at using percentages to compare two groups. And essentially, that's going to be questions 17 and 18 from the homework in our first chapter 2 homework, types of variables. And then we're going to look at some things called 5-figure summaries. And we'll get that done before the end of the day. And then we'll move on to our next section, our last section for this week, where we're going to look at histograms and 5-figure summaries and how do you describe data, things like outliers and skewedness and cool stuff like that. So let's jump right into our first kind of question, which is when you want to compare two or more groups, it's not a good idea to use the raw data. That just means the numbers that are in each of the categories. And the reason why that's not fair is, can you imagine I asked 200 women, I only asked 50 men. Can you see that the fact there's 50 men, they're always going to be less in each group because they're only 50 each year out. And so you can't say, well, 42 women said yes and only 4 men said yes and think that that's a fair comparison. So that's why we use percentages. It's a way of leveling the playing field so that when you're looking at two distinct groups, and it's the same information that you're comparing in these groups, that you can do it in a much fairer way. So let's have a look at question 17. And this is my version of 17. As you know, we all get slightly different versions. And this table is the age distribution for mothers in a certain country. And it's the age they were when they had their first child. And the two snapshots are in 2006 and the other one was in 2018. So you can see in 2006 in this country, about 21.9% of the women that had children were under 20. That was when they had their first child. And there's still not that many, but I guess slightly under 10% who were 35 or over before they had their first child. And if you look at 2019, can you see the percentages are clearly different? And what we're kind of looking at is there anything we can gain from this? And then we can see that represents maybe a trend. Right, if you're looking at this data, and since it's percentages, we can do comparisons with comparisons. Do you see anything going on here?
I see they're having more children later in life, I guess.
Yeah.
Or they're having, yeah.
Mm-hmm. I agree. What you're saying here is, if I just rephrase it, if you look at the 2018, aren't they typically getting their children later in life?
Right.
Their first child. Now let's see why I'm saying that. Right, if you take, for instance, the under 20s, isn't there half as many people who were under 20 in 2018 that had their first child? Now, if we move over to the next one, it's about the same. But if you look at the trend, right, as it goes up and then it tails off, do you see this one takes a little bit longer? In fact, isn't that age group the most common age group in 2018 to have a baby for the first time? And over here, it's a bit younger. Would you agree that there's a reasonable amount of evidence to suggest what we just said, right? That women in this country, at least, women in 2018 are waiting longer to have their first child. Now, do they still have people under 20? Of course there are, right? But there's less, right? Building up. That is actually, for Western countries, that has been a trend that's been going for about the last 30 years. Your mother or maybe your grandmother was maybe, late teens, early 20s when she had her first child.
Question, if I can. How does that relate to the population from that country? Is there any relation to the total population?
We can't tell for sure, but I would probably guess that there'd be less children born, because if you start later, you're probably going to have fewer children. I'm assuming that might not be true. So that would be a reflection that the population would probably end up being older and fewer children. That would be my guess. Can't say for certain, but that would be my guesstimate. Yeah, the idea of this change has happened a lot. It's social changes and things happen. The main reasons, I believe, are contraception has meant it easier for women to defer when they have babies, right? It's making it much easier for them. And careers, you agree a lot more women are probably thinking of careers, and then you want to get your career started, and then you'll have your children maybe a little bit later in life because of that. So they might be some of the factors for why that's the case. So good, cool data, right? You can use it in different ways. The first question is very easy, although it takes up forever and a day. It says, draw a bar graph of this data. Well, all I would do is say, okay, the under 20s is 21.9%. That's all I'm going to focus on. Under 20s, 21.9. That's not 21.9. Yeah, it's too big. It's not 21.9. Doesn't that look like 21.9 to you? Let's check the last one. Nah. Right, the only one that worked is that one. I bet you the other four work if I checked them. I only needed to check the first one. So you see how quick it was to do that question. I know it takes up a huge chunk of real estate, but the answer was pretty simple. And then they go down here at the end, and it's one of those pick from a selection, right? In general, we see that women had their first child in 2018 tended to be older. I might have to shrink this back a little bit. I lost that question. Yeah, where are they gone? Tends to be older than women who had their first child in 2006. The biggest difference is in the age group. Now, what's the biggest difference? So I'm going to go back up here. Right, here it's what, a 10% difference, a 4% difference, a 5% difference. That's what, about a 9%, that's a 3. This one here is the biggest difference, isn't it? So the under 20s. So I'll go back down here, and the biggest difference was in the under 20s, which shows a decrease of, oh God, I should think ahead before I scroll up and down like this. What's that? 10.
11.5.
Thank you. 11.5. The most common group in 2018 was, I mentioned that, but now I've forgotten. Is that one, right? Would you agree that's the one that had the biggest number? 25 to 29 group. Hopefully I'm not making you dizzy here. 25, and the other one was just one shy. Whoops, one shy. There. There's quite a few questions where you kind of fill in the missing words, essentially. Are we comfortable with what we did in that question? Does it kind of make sense where the data comes from? Okay. Now, here is one more of those. I'm only going to do part of the question, and then we'll move on. In the relationship, let's see what's going on. A sample of college students were asked how they felt about their weight, which is always, self-image is a very scary thing, especially for people like teenage girls. Very dangerous time in their life. You see all these things where you're built like a stick, and very few people are skinny like that, and it makes them whatever. Of the 141 self-identified women, 37 said that they felt overweight. So I'm going to put that in. 94 felt that they were about right, and 10 thought they were underweight. And then they asked 72 guys the same question, and 11 guys, 38 in this category, and 23. Right, that is what we call the raw data, right? Now, it's difficult to make comparisons between what men and women have opinion of their bodies based on that data, because there's different number of men, different number of women. Agreed? So I'm just going to pick the overweight number, but you should do it to all the others, right? And here are the percentages. This is them going down here. So for the women, for instance, overweight was 37 out of 141. And then you multiply that by 100. Now I just put that in just so you can see what my calculation is when if you want to go back and look at that. I got my thing here and I'll tell you what I've got. 37 divided by 141, and the answer is about 26%. I'm doing it to the nearest whole number. Well, okay, let's be more accurate. 26.3%. Okay. Now, if we do it with the men, it's 11 out of 70. Is it, how many men was it?
72.
72. Right. So 11 out of 72, and then make it percentage by turning it by multiplying it by 100. That guy, 11 divided by 72, that comes out as 15.3%. Now I'm going to rub out all the calculations so we can see the final result here. This is just one of the values calculated, right? You can imagine that, you know, if I did the others, and by the way, the answer that you want would go here, not in the table. I'm just putting it in the table because it's easier for me to see. Right. So you would be putting the raw data, the ones I like, the 94s and so on. But let's see what that one, just what that one says. Doesn't that look like a lot more women, percentage-wise, think they're overweight? Can you trust me if you did the underweight one? A lot more men think they're underweight. Right, self-image. It doesn't mean that you are or you aren't. They just ask you, do you feel you are? But when people are asked that question, don't they try and compare what they think their body is to the ideal version of what they think a female or a male should look like? And doesn't that cause discrepancies? Right. What that is telling me is that women think being overweight is something, right? That you're all thinking you're overweight, not all, but a quarter of you are. And in the men, it's a total under. Why are men's image, why do they not want to think they're skinny? That's kind of not a macho thing, right? You want to be, yeah, want to be manly.
Society says that we're supposed to be the strong.
Yeah, that's it. You know, there's no particular, I mean, if you went, I haven't heard of such a culture, but can you imagine? And there have been cultures. Do you know in the medieval days, a plumper woman was considered more attractive than a skinny one? And that was because that was a sign of health, right? Therefore, you would be, you know, likely to live and produce children. And so, you know, the concept of what beauty is has changed.
You need to make sure you're documenting under the correct encounter.
Oh. I am going
When it's
to
not there,
do a little interruption thing. There we go. I'm sure they don't want us to hear what they're saying. There we go. Are we comfortable about how you're going to answer that, the rest of that question? Do you see what I did? And then you can make up your own mind about, you know, fill in the blanks here, which is basically taking a summary of what's going on up there. Now I'm going to kind of bump out of this one for a moment and go back to, oh, we got some in the chat I should do. Someone just corrected me and said that, remember the biggest difference question? They went and said it was 35 and up because that difference is 11.8 and I chose the other one, which was 11.5. If those figures are correct, then I'm corrected, right? You subtract them and you find out which one was the biggest difference. Someone else has asked, what kind of TI-84 do you need? Don't need any particular one. Any one you can get will work fine. So you don't need to get a plus or a silver edition. That's the answer to their question. Now, if you do want to, and I suggest you get a hold of a TI-84, you can contact Cheryl Williams in Mesh by phone. And if you go to, I don't have her number on the top of my head here, but if you go to the Olympic website and you just type Mesh office, you'll be able to get her phone number. And you can contact her and see about getting a borrower. You can borrow a TI-84 for the quarter for free. So if you want to get one, you don't have one. So let's look at this thing called 5-figure summary. We are talking about quantitative data now. And in quantitative data, one of the things that you want to do is take a whole load of numbers and kind of organize it in some way that allows us to see what's going on. If all I do is collect 50 numbers and they're all jumbled up, and I go to my boss and say, well, I collected data on the ages of people who work for us, and here it is, and you hand him a piece of paper with 50 ages on it, he's going to look at that piece of paper and say, well, that's pretty much useless to me. I need to see some organization to it, right? Okay. So one of the ways that you can organize your data is by putting in order and then creating a thing called the 5-figure summary. And let's create one. I think it's always a good idea, if we can, to create data from this class. Now, this is a reasonably small class, so I think it won't take too long. 2, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15, 16, 17, 18. Right, there's 19 of us here, so I'll take account of that. But we might not all answer, and you do not need to. So I will start the ball rolling. I am 66. So anybody who wants to volunteer their age will tell me it, and if you don't need to. Okay, I got that person's age.
59.
A lot of them are typing in, which is fine. Anybody want to say them? I could do with a couple more.
37.
1, 2, 3, 4, 5, 6, 7. 2 more would be good. Lauren, what you got?
I turned 26 like 2 weeks ago.
Ah, happy birthday, kind of belatedly. 1 more. If we could get 1 more, it'd be great. Did I miss some in the chat? Maybe you've already told me. It looks like we could have. Let me check.
I tried to type in.
I missed one. There, we got it. I'll use that one. I may have missed some of you, but that is fine. I've got some good data to work with. So let's suppose we want to know what are the ages of our class, right? What do they look like? And the first step is what I just did. I got all your ages, except, would you agree, right now it's just a list of numbers. You don't get a really good feel for what's going on. So I guess the first thing I would do is put them in order. So I've got a 17, then I've got an 18. I got a 16. What's the 20s look like? I got a 24. I got a 26. Got a 37. 39. I got a 47 and a 66. 1, 2, 3, 4, 5, 6, 7, 8, 9. Perfect. So what I'm going to show you here is 2 different ways of creating the 5-figure summary. In a lot of the questions in WebAssign, they just tell you these numbers, but it's like magic. They just appear out of midair. I'm going to actually show you how you create these numbers in 2 different ways and kind of what do these numbers tell you. So first number is called the maximum. There's a guy called Q1. There's a guy called the median. Right, these are all numbers. And the median is sometimes called Q2 as well. Then you've got a guy called Q3. And lastly, You've got the maximum. Well, let's get the two easy ones out of the way. Would you agree that the youngest person is 6? Whoops. What am I saying? Max.
The minimum, right?
Min. 16, right? And the maximum, there you go, is me. 66. So far, so good. Now, the next number you typically calculate when you're doing it by hand, which is the first method I'm going to show you, is you find the middle number. The median is the middle number. Now, right now, there are 9 people. When there's an odd number of people, like 9 or 13 or 127, there's one guy in the middle. Watch how I count it. Right, you go 1, 2, 3, 4. Do you see that guy there is the middle? That guy there is the median. Okay. Now, the median is basically the person right in the middle of the class. So whoever is 26, whoever said they are 26, you are kind of the average, kind of in the middle of the road kind of age for this class, right? You're not definitely not the oldest, you're definitely not the youngest, you're bang in the middle for this class, right? Different classes, you'll be in a different place. Now, Q1 is called the quartile, the first quartile, and Q3 is called the third quartile. And quartile is useful because what you do here is you cover up the middle guy. Do you see now what I've got is 2 separate groups. I've got the small half and the big half. And the middle of these is called Q1, and the middle of these is called Q3. But there's a problem. When you have an even number of numbers, there's not one guy in the middle. Would you agree that there's kind of a draw? Both of these are in the middle. Would you agree? I don't think 17 is in the middle. I don't think 18 is in the middle. I think both of them are kind of in the middle. So how do you think you get round the problem of choosing the middle one in a story like this?
Do you do like 17.5?
That's exactly what you do. So Q1 will be 17.5. Now, if you go over here, there's quite a big difference, but nonetheless, you do the same thing. To get Q3, you pick somewhere between here and here. And I'm just doing this on my calculator because I don't trust my brain. Oh, 43. And that's called a 5-figure summary. So if I was looking at just this and I didn't know these numbers, and I said, oh, you've got a class, do you? And I said, yeah. What's the 5-figure summary? And I showed it to someone. They'd say, oh, so the youngest in your class was 16. The oldest, that's probably you. Yeah, you're right, it's me. It's 66. What's the typical person in the class? Oh, they're about 26 years old. Now, 17.5 and the 43, can you imagine a little number line where that's the start and this is the finish? And the person in the middle, right, Q2, the median, is about 26, and a quarter of the way along and 3/4 of the way along. Do you see how it's called quartiles? Do you see why that name is being used? If you look at 17.5 and younger, about a quarter of the people in this class are 17.5 or younger. Half the class is 26 or younger, roughly. 3/4 of the class are 43 years or younger, and everybody in the class is 66 or younger. You see, it's kind of like little signposts along the road. And what that does is it gives you a kind of, with 5 numbers, it gives you a breakdown. Okay, 9 wasn't a big, but can you imagine it was 900 numbers? Wouldn't a 5-figure summary still give you a good picture of the overall spread of, you know, where the age groups are? We go with that. Now, I promised you 2 ways to do it. The second way is quite long, and actually I've decided to do it a slightly different way. I'm going to show you on a calculator app I've got because the screen's a little bit bigger. And you might want to look this video up again, just maybe to see this bit, or even the bit I did before. So what we're going to do is we're going to hit the start button and we're going to choose number 1, edit. And what you do is you type in everybody's age, and you don't need to put them in order. You can just put them in, you know, whatever way they came out. So this is the way I collected them. So that's good. You don't need to put them in order. If you're doing it by hand, however, you have to do the step where you write them down again, but this time in order. I'm slowly, because I'm not that efficient at typing. Right, that's the data in. So I'll do second quit, then show you where it came from. I hit the start button, option 1, edit, right, and there's my data. So far, so good. Right, and let's get out of that with second quit. Hit start, calculate. So I'll do that again. It's too quick. Hit the start button. Right now it's on edit. I'm going to move it over to the right by hitting this button. And I'm going to choose 1 variable starts. And I'm going to hit enter. Now, in the modern ones, this is a little bit different. You have to do a little bit different, but that's fine. In my old version, you have to type in L1 here. And although you might not see it clearly, L1 is a blue guy on the 1 button. So in my case, you hit the blue button 1 and you've got it. And some of you have a little menu that you go through. So when I hit enter, I am going to see lots of statistics based on that data set I just typed in. And I don't care about these right now, although later in the quarter I will. I'm just going to hit the down button. Can you see my 5-figure summary? 16, 17.5, 26, 43, and finally 66. Are we good? So you can do it by hand, or you can plug it in with a calculator or whatever. You know, some people like doing it by hand, some people prefer the calculator do it. Any questions about how to calculate a 5-figure summary? Are we good?
I have a question about number 19 because it's within the same realm, and that is the final question. The 2 final questions, I couldn't understand the terminology. It was the proportion of females who had driven 87 miles per hour faster, and then the same for the second one, or the number and the proportion. I was wondering if you could explain that.
Okay, let's wind that back. What section is the question you're having a problem with?
Number 19 for chapter 2, types of variables.
19. Oh, that's quite near the end. Let me have a look at that one. Keep going, keep going. Haven't got there. Oh, we are about to do that question. So let's do it. The 2 questions that are, oh, I should have called them 18 and 19. I did, they are, they're here, they're 19 and 20. So let's show you them and try and make sense of how they phrased it. So here is a 5-figure summary for the fastest ever driven data. Okay. They asked 88 guys, what's the fastest you've ever driven a car or a motorbike, I guess? And they asked 100 females the same question. And these are the 5-figure summaries. So this guy here is Q2, the median. This guy is Q1, this guy is Q3, this guy is the max, and this guy's the min. All right, they may not have written them down with the names I called them, but the guys they're calling the extremes, the small one is the smallest, and the big one is the biggest. So see, for guys, one guy, the fastest he said he's ever driven was 56 miles an hour. So he's probably still alive today. And this fella said he's driven 153 miles. Now, he may be just a liar or dead, but one or the other is probably true by now, if he continued doing that. The things they're calling the quartile, the small one is Q1 and the big one is Q3. And the median, yeah, I called it the median, right? So if you imagine these numbers going in a big, like, tunnel, 56, 96, 111, 117, 153. Do you see my 5-figure summary? Right, starting here, going up and curving down. You see the numbers, the order? So they're there, right? They might not be called everything, but they are there. And here's the females. In this case, we don't need to think about turning things into percentages, like what percentage said this or what percentage done that, directly at least, right? Although it would be helpful. We could just look at the value itself, right? So the fastest speed driven by anyone, well, I would say it was 153. It was a guy that did it. The slowest of the fast, God, that's bad English. The slowest of the fastest speeds was this one. That was weird English, but that's what they want. The speed for which 1/4 of the women had driven at that speed or faster. I would have said the top 1/4. Now, if you're talking about the top 1/4, wouldn't that be another way of saying that speed? So I'm putting in 96. Oh, darn it, I can't put check, but never mind. Now, the proportion of females who had driven 88 miles or faster. Right, 88 miles is the median. Right? Remember, the median is exactly in the middle. Doesn't that mean half the women have went faster, half the women have went slower, right? 88 miles. That is the middle. So what is the proportion of those? Well, 50%. Now, if they said percentage, I would type in 50%. But if they say proportion, they just mean as a decimal, or I would accept a half. But I suspect they were wanting you to say and the number of females who had driven 88 miles. Okay, that's an interesting question, but it's not as hard as I thought it was going to be. If there was 100 women in this sample and half of them went 88 or faster, wouldn't that be 50 of them? Be a better question if they'd done it for the guys. 88 of the guys, right? And the question would be, how many of them have done 111 miles or faster? And the answer is half of them. And wouldn't that have been 44 guys? Did that answer, can't remember who it was, Ariel's question?
Yes, you did. Thank you. I was
Okay.
confused. I was like, I
Oh
don't
God, I'm
understand
not
the
surprised.
terminology.
Well, even the way they phrased it, the slowest, fastest, I mean, that just sounds wrong, but I know what they meant. Okay, this question 20 is basically a duplication of question 19, but with different Is it different numbers? Yes, it is. It just has different numbers. And you're not being asked to do numbers this time. You're being asked to use an appropriate summary. So using the appropriate measure of location, which is the median. Oh God, sorry. Using the appropriate measure of location, which is the something we can see that the males typically have something faster speeds ever driven than females. Right. Higher, faster speeds. And I'm using the median. The middle for a male was 104 miles an hour. The middle for a female is 88. Right, so using the medians, wouldn't that be evidence that males just go faster? Does that make sense? I'm seeing some notes and some puzzles. Lauren, what's not making sense?
Wouldn't it technically be the quartiles though? Because it's 97 to 79.
The quartiles are telling you the same answer, yes. But I would always use the median. And the reason why I would choose the median over the quartiles is the median is like the typical person in each group. The quartiles are a little bit more extreme, you know, the bottom a quarter or the top 3/4, right? And so I think it's just a bit fairer, can't think of a better word, to pick the middle of the road person, right? The typical person in the males was 104 miles an hour. The typical one in the females was 88. Do you know data like this explains in some part why insurance premiums are different for different people? Why, if you're under 21, is insuring your car more expensive than if you're over 21?
Because the data shows that under 21, you haven't developed the thing in your brain that controls impulse control, so you're more likely to be reckless versus people who are over 21. It's, you know, they're less reckless.
Now, I don't know if this is true, and maybe it's not true, but it probably should be. Women should get a lower rate than men, a lower car insurance rate, based on this data. Would you agree if this data is true in the big population? Aren't women safer, as in drive slower, which tends to mean less accidents, I would assume, right? Has any of you found that out? Have you and your brother, maybe you're twins, and your brother ended up paying a higher premium than you did, and the only difference you can think of is your age? It's not your sex, not your age. Does anybody even know if that's true? They may not do it because it's probably a law that you can't discriminate on basis of sex. Right? You can't say, I'm going to give a woman a better deal than a man because she's a woman, or vice versa, right? Wouldn't the women complain if men got something better than the women? Wouldn't you be saying that's not fair? So maybe that's why it doesn't happen. But according to the statistics, it would make sense if they did so. Age doesn't count, so they can actually say you're too young to be safe. And even if you could say, I'm the safest driver in the world, they're still going to ding you for your insurance, aren't they? You're still going to have to pay more.
Yeah.
And if you've ever driven on the roads, I've seen some real dumb 40-year-olds driving, right? So age is not a prerequisite for intelligence or being sensible. So I once saw, and I'm not being sexist, and it sounds like it, but it just happened to be a woman. I once saw a woman with a book of some kind on her lap, one hand driving and the other hand was eating. And the only reason I see that is because when I'm in the car, my wife refuses to let me drive. She says I'm crazy. And so I sit in the passenger seat, so I see all sorts of things I wouldn't see when I'm driving. So there's some dumb people in this world, whether you're young or old. Okay, let's move to our new section, our final section. And I can tell you a little bit about what it is, and then we'll start looking at some of the questions. We're going to look at histograms. We're going to return to some 5-figure summaries again. We're going to look at shapes of data, and we're going to look at things called outliers. I'm going to do the big picture right now. This is all going to be on quantitative data. Right, so whenever you talk about histograms or 5-figure summaries or the shapes of data or outliers, you tend to almost exclusively are talking about data that is numbers. So let's suppose, just for argument's sake, and I collect data on 5, 6, 7, I think I'll do one more at least, 8-year-olds. And I ask them something. What would I ask them that would have a number attached to it? I found their average height. I have no idea what a 5-year-old is. So I am making this data up totally. So if it's weird, just pretend it's right. So the average 5-year-old is 24 inches. And these guys are 30, these are 37, and these are 42, right? So I've got a whole load of data and I want to put it into a kind of chart of some kind. Along the bottom, you could put age, and up the top, you could do, say, height. And what you're looking at is 5-year-olds, 5, 10, 15, 20, 25, so just a little bit shy. 6-year-olds, 30. Need to keep going. 7-year-olds, 37, it's about here. And lastly, 8-year-olds is 42, which is about here. What you're looking at here is called a histogram. It's very similar looking to a bar chart. There's one major difference in this picture. What's the difference between this and a bar chart? Visually, what can you see that's different?
I think a bar chart can be a little more random.
Well, that's true, it can be. Do you know, maybe it's so obvious that you're just not noticing it, because that's very easy to do.
It's organized from low to high as far as the age.
That's true. Nothing wrong with that, it's also true. And that's true in all histograms. I guess I'm just not phrasing it well, that's probably me. There's no gaps between them.
Yeah.
Is that what you're going to say, Lauren?
Yeah, that's what I was gonna say.
Yeah. If you were doing a bar chart, wouldn't you have a guy, a space, a guy, a space, a guy, a space, a guy, a space, right? It doesn't seem like a very significant difference, but it is a difference. Histograms, as you said, Robert, are in order. They're always in order. So see the horizontal, it always starts with a number and then goes up, 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 up. And typically this will be a frequency and it goes up and up. So if I was, let's take another example over there. Let's suppose we did a chess club at a high school, say, and I don't know if you can be 15, but let's say you are. There's their age. And here would be what's called the frequency. That's very common. And there was 3 15 years old. There was 7. There was 11. There's an 18-year-old. So there were 5 of them. I don't know if you can be 19. I guess you could be at high school if you repeat a year. There's 1, right? This would be your usual collection of data. 15, 16, 17, 18, 19. And can you imagine that you always do the variable, the descriptive variable along, and very often what's called the frequency goes up the way. In this case, we would start with 15, then 16, 17, 18, And finally 19, and 2, 4, 6, 8, 10. So 5, that would be about 3, 6, 15, 16 was about 7. It's about here. Then it's 11, which is way up here. Then 18, that's about 5, it's about here. And then 1 that's here. What would I have done to this histogram if one of these age groups had 0? Let's suppose there was nobody 18 years old. What would that look like in a histogram if nobody was 18 years old? What would you do?
Remove entire.
Yeah, see that guy there? You would still have the 18. But you just leave it as a blank, right? When you do categorical data, if nobody said they like red, wouldn't you probably not even write it down? Because nobody said chartreuse and nobody said black velvet and who knows what colors in the world there are, right? Don't you just typically only write the things that somebody said, yeah, that's my color, or that's the country I've been to? You typically don't bother in bar charts to write the zeros. But in histograms, you always write down any data from your start to your finish, at least, that is that. I don't need to write the 14s and 13s or the 98s and 99s, because we only start and finish. And anything that's between these does get included if it's 0, right? And that's another little change. So the data is in order, there's no gaps, and we leave zeros in. We don't omit them. We have a space for the 18 to go, and there is nothing in there. So let's talk a little bit about shapes. And what I mean by that is actually the shapes of your data. And the typical things that you're going to be looking at are histograms. But there is also things called dot plots. I don't think we get any in this, but you will get them in the future. And we have things called stem and leaf. And what we're looking at here when we talk about shape of data is that if you want to describe visually what the histogram looks like, we have some terms that we use. So for instance, if I was doing a histogram and it looked like this, which is basically a single hill, that would be called symmetric. So if your data is one hill or it's got a nice balance to it, we'd call it symmetric. Instead of drawing all these rectangles, we typically kind of abbreviate it to like a curve. So can you imagine that's trying to represent this? That's what symmetric looks like. A lot of data is symmetric. Do you know if I collected the weights of 200 adult males, right, and put them into groups and categorized them, it would probably have that shape, right? That would be kind of the average shape for male, weight for a male, and this would be a very light male. This would be quite a heavy male. That's what symmetric looks like. Now, there are two other guys. Data sometimes looks like this. And sometimes the data looks like this. And these shapes happen quite a lot. And because they do happen a lot, we have names for them. This fella is called skewed to the right. And this fella is called skewed to the left. And you might say, that's a funny name. I probably would have called it the other name. But this piece of the shape, you see this bit that's tailing off, it's actually called the tail. And when we say skewed to the right, we're really saying the tail is on the right. It's skewing to the right. And if it's on this side, can you see how it's skewed to the left? So if you want to remember which name to use, because it's easy to mix those two names up, think about what the long skinny tail is doing. Is it tailing off to the right? Skewed to the right. Is it tailing off to the left? Skewed to the left. We go with that? Just terminology to describe what histograms look like. Now, can you imagine these being lots of little rectangles? It's just easier to draw curves than it is to draw this all the time, right? So far, so good. Give an example. If I gave a really hard test, it probably would end up looking like this. Can you see a lot of people didn't get very good scores, and then a few people got really good scores? Wouldn't this be the total opposite? Wouldn't this be an example of a very easy test? A lot of people getting high scores and not that many tailing off with small scores. If you were doing what you might call a fair test, shouldn't it have a shape more like this? So when you're looking at data, it can sometimes give you an indication, for want of a better word, of fairness. Yeah, that's pretty fair. That seems reasonable. Now, another feature that you sometimes want to describe in a histogram. This isn't its official name. This is my name for it. Can you imagine a histogram that climbs up and then climbs down, then later on climbs up and back down again, right? It's basically got two hills. We would describe this histogram as bimodal. Bi is the same word from bicycle, meaning two. Now, could you imagine a situation where your histogram had three hills? Anybody want to guess what you might call a histogram that had three distinct hills in it?
Trimodal?
Yeah. And the good news is we don't call it that.
Oh.
But you're right. If you did, I wouldn't fault you for it. And quad modal and pentamodal, it gets a little bit. So what we just do is we call it multimodal. So you can have one hill, and if you've got one hill, won't you probably be symmetric, skewed right or skewed left, or just don't have any shape at all, right? You got one hill, but you're probably going to be one of these three. On the other hand, if you've got two hills, we'll call you bimodal. If you've got lots of hills, three or more, we just say they're multimodal. And so if I, for instance, I have some data in my mind and it's unimodal, just means it's got one hill, and it's skewed to the right. That's all I've told you, right? One hill and it's skewed to the right. Are you thinking of something that looks like that? Do you see how I use words to describe something that's quite visual? Skewed to the right. Ah, one hill. I don't even normally bother to tell you it's unimodal. Do you know if I said it's skewed to the right, you're going to assume that it's unimodal because we all do. So far, so good. Right. Now, still on the describing shapes of data, there is a term that you may have heard somewhere. They're called outlier or outliers if there's more than one. Anybody heard the term that data point or that person is an outlier? Doesn't it? Yeah.
I heard, isn't it something like it's out of the ordinary, like
Yeah.
not normal?
Oh, I like that phrase. I'm going to use it. Outliers, out of the ordinary, not typical, not usual, right? Phrases like that. Now, I want you to imagine that I'm going to put in rectangles this time. Mostly I don't like doing it because they take forever. Can you see my outlier? Out of the ordinary. He's on the outside. I'm trying to think of other phrases. Would you agree that that's a big outlier, meaning that its score or its height or its weight, whatever this is measuring? We're going to measure frequency on this side. Right. Frequency is how many people had that number, right? Or said that answer. He is an outlier, she is an outlier. And that's a big outlier. Isn't that person over there an outlier? When you look at these, what visually is the clue that you're talking about an outlier?
Their separation from the norm.
Yeah. If you think of this as being the data, right? The normal data, right? Where everybody lives. And there's a good separation, and then you see a little guy stuck in his own. Is it possible? Well, it actually is, so I won't ask that question. Isn't it possible to have two outliers? Yeah. Can you have a big outlier and a small outlier? Right. No reason why not. Couldn't you have none at all? Suppose that was my data. Wouldn't that just be normal data and nothing special? Now, we have to be a little bit careful about who is an outlier. So I'm going to show you a problem. Imagine I take this box and I move it to here, right? So it's now here. Would you call him an outlier? Okay, I agree with you, I would. Why? Suppose I move the box to here. Would you call that an outlier? No, there's no separation. Would you agree? It's just at the tail end of the usual data. So I'm going to put a no. Would you agree that there's some gray area between there and there where a yes turns into a no? And you could say, well, is one gap enough? Right. Actually, let me do that data again because there's a lot of distraction. Let's suppose I had some data that looked like this. Would you count that guy as an outlier? The answer is no. You shouldn't count that guy as an outlier. I know there is some separation, but it's not some that we're looking for. I think the word we're looking for is a lot of separation, whatever a lot means. Right?
I'm sorry, could you repeat that? My internet cut out for a bit.
At this point here, yeah, what I was saying is when you're looking for is a particular data point an outlier, it's not good enough to just have a little bit of separation, right? A little gap. That is not an outlier, right? This guy here is not considered an outlier. He has a little gap, but that's not a lot. What you want is a significant gap, right? A big gap. Yeah, like here, right? That's an outlier. Which does mean, what I was saying, don't you have a kind of moving target? Right, see that guy that I'm putting a little dotted line over? This one here. Forget all the things that are happening around it, right? Forget all these other things, right? Is that guy there an outlier? Some of you will say yes, and some of you will say no. Can you see that there's going to be a judgment call eventually? If something's miles away, we all say you're an outlier. If something's almost on top of it, nope, you're not. But between those two extremes, there is the possibility for a judgment call. Later on, we're going to show you how to avoid the judgment call. There's a test that we can use on this value, whatever that number is. And if it passes the test, it's an outlier. And if it doesn't pass the test, it's just considered a normal bit of data that just happens to be a little unusual, but not significantly so. But right now, you're just going to do it by eyeballing, right? Yep, you look weird, you're an outlier.